Good afternoon, everybody. It is indeed a pleasure to have this opportunity to introduce my chief and colleague, Jim Tucker, to give us a presentation today. Something that many people may not recognize is Jim is really dedicated to building the next generation of scientists and nurturing them. And I have been working with him for about the last 15 years. And it has been a pleasure working with him, given that I'm still here working with him. That tells you that he's a very amenable person to work with. The other thing I would just want to point out is the work that Jim has contributed to in terms of supporting NASA's mission to planet Earth, specifically on vegetation monitoring. He's a pioneer in this work, and he's going to talk himself about many things he has done. But I would like to point out one thing is one of his papers that was published in 1979. It is now a classic, required reading for anybody doing remote sensing of vegetation. And it is been recognized as one of the most highly cited publications by the science. The other thing is Jim has many honors, but especially one that many people may not know about is the Mongolian Fellowship Award. I don't know how many people have ever gotten that. The other award that many people may not be aware of is Jim received an award from the Royal Danish Geographical Society from the King of Denmark. That basically tells you we have a giant with us. So on that note, let me present to you the chief, Jim Tucker.
Thank you, Asaf, for a nice introduction. First of all, I feel as if I'm in a movie like Groundhog Day because I previously gave a Maniac Talk, but it wasn't recorded, so I was asked to do it again. So then I came to see as many talks as I could, and I have to tell you in advance, I can't top the drama of Gene Feldman's talk, where Gene Feldman got his start in the Peace Corps as a marine biologist because his predecessor was eaten by a great white shark or some shark and carried away, never to be seen again. And so I don't have anything nearly, well, I'm simply light years or many orders of magnitude away from anything that dramatic. But I'll start, and I have a few unusual things which I've done, many of, or most of whom are far behind me, thank goodness. So the title of my talk is From New Mexico, where I'm from, to the Pawnee National Grasslands of Colorado, and then to NASA Goddard Space Flight Center. So where I'm from in southeastern New Mexico looks kind of like this. It's where the Chihuahuan Desert runs into the Guadalupe Mountains, which is a southern extension of the Rocky Mountains. And as we say in that part of New Mexico, we're so far from heaven but so close to Texas. And I have vivid recollections as a kid on my bicycle driving down Main Street, which was Canal Street because there were ditches which lined it, irrigate trees and things. Buses from Texas, principally I think sort of church buses going to the mountains of New Mexico, would pass through, and they would always be singing in our town and other New Mexico towns, "The eyes of Texas are upon you," or "The yellow rose of Texas." And I would just puzzle by this, and then I realized there's a bimodal distribution of people from Texas. There are the fairly religious people, or very religious people, who aren't much fun, and then there are the good old boys and good old girls. And I was very pleased to realize that. But anyway, so I'm from southeastern New Mexico, and my sister had gone to school at the University of Colorado, and I realized Colorado was a lot of fun because you could ski and you could drink beer when you were 18 legally. Wow. So I went to Colorado State University. Here's a picture of Fort Collins, Colorado, with Long's Peak in the background. And And then I graduated in biology, really pre-med in 1969. Wasn't sure what I wanted to do. So I found a job through a former high school teacher working for what is now Visa. At the time it was Bank AmeriCard, which is the credit card company. And so I worked first at Colorado National Bank in Denver for a few months, and then went to Albuquerque where I worked. And I was doing office work, and I was also on weekends to make extra money. I was a bill collector. Well, I don't think I ever got anyone to pay, but this really impressed upon me that I didn't want to do work like this. And I also felt very sorry for all the people who had received credit cards in the mail, usually without them asking for them. They had used them, and then they had to pay. And so I had to endure many rude people, their dogs, things like this. And then it dawned on me, someone said, well, look, for every card which you get back from these people to sort of stop the hemorrhaging of money from the First National Bank of Albuquerque, we'll give you 25 bucks. So I would just tell people, look, I understand you can't pay, but just give me your card and I'll leave you alone. And so I was able to get 5 or 6 cards, but then I thought, this really sucks, and it's not much fun, and so I'm going to go to graduate school. So then I returned to Colorado State University and was working as a truck driver for $1.50 or $2 an hour in a commercial greenhouse. And I read in the student paper at Colorado State University of a new remote sensing program started by a fellow named Lee Mueller, which was associated with the grassland biome of the U.S. International Biological Program. So I called him up and said, I read this blurb in the newspaper. He interrogated me over the phone. And then he said, well, what are you doing? I said, well, I'm working in a greenhouse. He said, well, come down and see me. So I came down, and there was his teaching assistant, a fellow named Tom Wagner, if any of you know Tom, didn't show up, but he went instead to Nepal to do something, and Lee Mueller thought that I knew about horticulture because he loved plants. I don't know anything about horticulture. He told me later he almost fired me when he realized I had no knowledge of flowers and horticulture, but somehow he didn't. Then Lee Mueller, who unfortunately passed on 2 or 3 days ago, I tried to call him to get some other slides, and his wife told me unfortunately he had passed on. He's on the right. But we were working at the Pawnee National Grasslands, and we were collecting hyperspectral data, and we would measure areas like this, and then we would clip them and then look at the chlorophyll concentration, of the leaf water content, of the green vegetation fraction, the dry vegetation fraction, and look at the green and the dead fractions. And then we would, and then I was in charge of the analysis, and because I was the only biologist in the group, and so we would then look to see what we could back out of this. So here's the Pawnee National Grasslands, and once again, I was just lucky that we were working on an extremely simple land vegetated surface, because there's no woody vegetation and everything is herbaceous, and it's either green or dead or somewhere in between. And so this reduces the complexity, and we were trying to estimate how much grass is growing, what the total photosynthetic activity is, because this is the energy which then cycles through the ecosystem to the consumers like cows, buffaloes, insects, and then secondary consumers which eat the primary consumers, and so on and so forth. So we had a field spectrometer in a trailer, this trailer, out on the Pawnee National Grasslands. It looked out through this port right here. We had to improvise a big piece of styrofoam from the rubbish, cut a port in it, because that would keep the interior of the trailer cooler, and we had a small air conditioner which you needed. And so here was our hyperspectral instrument. It was an EG&G spectrometer, 5 nanometer bandpass, which operated from 350 nanometers in the ultraviolet out to about 13 or 1400 nanometers in the shortwave infrared. It was interfaced to a Hewlett-Packard 2100 mini computer. Now, for many of us here who started working on mini computers or doing programming in the late 60s or 1970s, early 1970s, this only had 8 kilobytes of RAM. It had no disk drive, so you had to be extremely efficient in your programming. and also store what data you collected in RAM as well. So I don't think people put things into common statements or whatever the equivalent in C++ for a common statement is, but in Fortran you need to do this so you minimize how much core you use, or at least you needed this before. And then the input-output was paper tape, and we had a 2-pass Fortran compiler, and you had to type out your program on a teletype, and this paper tape came out. And then you had to start every operation of the spectrometer mini computer to collect data by actually entering the register of the first line of your compile code, and then press load, the switch right here, and then the program would start. But this was light years ahead of what people had to do before. And once again, we used a teletype to punch paper tapes. And believe it or not, this was the state of the art. In fact, people were very envious of our operation because we could collect quantitative data again and again and again. You could write very efficient programs, and it was a lot of fun. So, but this is interesting to me because this is the paper tape punch. This is a paper tape reader. So all of our output, all of our spectral curves came out as a paper tape. Now, this also made great confetti when you had to go to graduate students' weddings. Because when you punch out the holes in the paper tape, you end up with this big thing of confetti, and frequently we would get bored and have confetti fights. Here is a teletype, and then here is the control panel again of our HP 2114A computer. Now, here's an interesting picture of a Bill Paul teletype and paper tape circa 1968. Well, yes, this is Bill Gates. This is Paul Allen. Here's a teletype, and they're programming. They're actually writing a program on a teletype machine. They'll get a paper tape, which then they can load into whatever computer they were working on. So if you're in Albuquerque, there's a very interesting exhibition at the Museum of Natural History and Science in Albuquerque right now. It's devoted to the early days of Microsoft in Albuquerque and the first personal computer, the Altair computer. And the fellow in charge of that was a fellow named Dr. Roberts, who was a physician. So this is what paper tape looks like. All these holes in it. It would frequently tear. You would have to very carefully line them up and use a special Scotch tape on it. And so then after paper tape, we then went to magnetic tapes. At one time, my office in building 16W held 3,000 or 4,000 of these paper tapes, big rolls like this. Or rather magnetic tapes. Here is a 1600 BPA, 1600 bits per inch a magnetic tape, and I have several other props too. But anyway, so what we would do is go out on the shortgrass prairie, we would measure areas like this, and then we would destructively sample them. And this is the basis for the energy flow in grasslands, which are probably the simplest, as I said, of most terrestrial ecosystems. The tundra is comparable. But clipping is very limited in time and space. We were trying to find some way via remote sensing to extend these measurements in a continuous way over the landscape. Okay, so here are some of the curves of the spectral curves we collected. So we start in the ultraviolet down here. We go through the visible from 400 to 700 nanometers, and then on this particular grading of our hyperspectral spectrometer, at 5 nanometer wavelengths, we have all of these reflectivities. Here is a data dropout, but this happens sometimes. But the fact was we could go out, and in 3 or 4 days we could measure and sample lots of areas. And that then enabled us to hone in, first of all, on 2 wavelengths. One band in the red where we have very strong chlorophyll absorption, and the other slightly beyond the upper limit of our vision in the reflective infrared where there's no absorption. And you could use those 2 wavelengths in combination because variations in the downwelling solar flux are minimized if you're fairly close together in a spectral sense. Hence, we were able to use them. So we would take these 2 measurements. Here's, again, on the right is the near infrared. On the left, you see this very strong chlorophyll absorption down like this. And then we combined them into various linear combinations or ratio combinations. And we ended up using a very simple one, which other people had proposed, but didn't understand why it worked. And that was just to take the difference of the 2 bands and then divide it by the sum, where you bound things between -1 and +1. If you take a simple ratio like this, it can go all over the place. So if you have some sort of normalized difference, this enables you then, once again, to bound it from -1 to +1. At the same time, I also did some modeling work. Now, this is a very advanced one-dimensional leaf model. And it's stochastic, but it's interesting throwing things together in some sort of simulation sense to see if you get out what you expect to get out. So very early on, it was obvious that within leaves there are two processes. One is scattering, and the other is absorption. This is true about almost any medium which you're studying, whether it's the atmosphere or the oceans or whatever. Those are the two processes optically which happen to what impinges upon things. And of course there's also fluorescence and a few other things, but we disregarded those, or at least I did in this one-dimensional model. So you're able to then run this as a function of wavelength at every 5 nanometers from the ultraviolet out into 2.5 micrometers, and you simply, when you do this, you could reproduce then what you would expect in terms of a green reflectance curve from vegetation based upon the various parameters. This is not some cavern, but this is the interior of a bean leaf magnified about 2,000 or 3,000 times. You're actually looking at individual chloroplasts, and this is an intercellular airspace, this cavity, because you need to get carbon dioxide into leaves. So then the chloroplasts absorb the shortwave flux in the visible. That drives photosynthesis. Within the chloroplasts, the cells are hydrated. That's where the water comes from, but that's the energy which drives things. Okay, so then I finished my PhD and then came to the Goddard Space Flight Center. So I'm kind of inbred in the sense that I went to one university and I've worked at one place, here, other than my banking, credit card, bill collecting experience. So I came to Goddard, and before I did, or when I got here, the people I worked with, the engineers, had not written up any of their work. So I said, well, this is crazy. You should write things up. So they gave me what they did. I added some of the experimental data which we had collected and I'd been in charge of to show what they were doing and how you could use it. And then I was the most junior author on these publications, and we published an article on this really simple handheld 2-channel instrument. And then when I was published in Applied Optics, people started contacting me. Why don't you come and try it out where we are? And this was used to look at how much grass biomass was there. And people realized clipping is a pain, and you know what? It's time consuming, and plus you can only do so much, and you can injure yourself by the clippers, etc. So then as a postdoc here, I was permitted to, at my own expense, to travel to Europe one summer. I mean, hardship travel. First I went to Iceland, then I went to England, then I went to Wales, then I went to Scotland, then I went to Sweden in 2 places, and then I went to the south of France, and then came back 3 months later. But in the process, I was able to check in many field settings this instrument and how it worked, measuring red and near-infrared reflected light. So starting with hyperspectral data I feel are a wonderful research tool, but if you want to employ techniques via remote sensing, you don't need all those wavelengths because most adjacent wavelengths are very highly correlated. So you can reduce the number of bands which you're operating upon, have a wider swath width, a finer spatial resolution, and then with this instrument we realized there's a lot of information in the time domain, how things vary, how things co-vary through time. At the time we were doing this, we only had Landsat, which was phenomenal, but that gave you the spatial detail. And so we were interested in new ways to exploit the time domain for land remote sensing. So in fact, this picture, in case you wonder, Brent Holben was down in Puerto Rico, and Brent and I were roommates in graduate school. And so I brought this instrument down, and here we're making spectral measurements on the floor of a mangrove forest to see if we couldn't estimate the leaf area index of the mangrove forest by the quality of light on the forest floor. So we did this in tropical forests, we did this in mangroves, we've done it all kinds of places, but especially in grasslands and herbaceous systems. So in Iceland, this is probably one of my least known papers where I'm Compton Tucker, but in Iceland everyone goes by their given name, and then if you're a man, you're the son of your father's given name. So I would be Compton Comptonson. Or if my name was Dorothy, then I would be Dorothy Adele's daughter, because Adele was my mother's name. So anyway, so this is a paper we published there from doing some work in Iceland. The thing about Iceland was conditions changed all the time. Every few minutes, it would be a different condition. So for example, overcast, very cloudy, sunny, a mild wind, so-and-so, like this. But these two spectral measurements, very close together, held together in a quantitative sense. These were radiance measurements. So I thought, wow, maybe there's something to this technique after all. So here's a picture of this very simple two-channel instrument. It's held together by rubber bands. And you had to have someone working with you who you would call the radiance numbers out to write down in a book. Very low tech, but it was mobile, and you could go all kinds of places. Then, when I came back to Goddard, some engineers here said, well, why don't we build a better instrument? Here's one of our three-channel instruments, and here we're looking at winter wheat. And just by coincidence, someone gave me this when I gave a talk at the University of Maryland. Here's one of these instruments. It's a very simple three-channel instrument, red near infrared and shortwave infrared. And so this is what we used for several years to get more field data. But the goal always was to move to satellite data. And that's because, well, okay, so this is an experiment we did on winter wheat. This is winter wheat in early March. And so Brent Holman and I and two of our co-workers from the USDA went out, and Brent and I, and we enlisted, if Brent wasn't here, we would always bring other people with us to help. So we had a lot of help, and we would take spectral measurements every sunny day. So if it was sunny, we'd look out the window. We were in building 16W, no windows, we had to look out the door. And then we'd go out in the field over here to Bellsville and make measurements. So we were able to make measurements with an average every 3 or 4 days. And from this, we were able to define what these two spectral measurements, where you simply difference them and divide by the sum, and how this varies over the growing season for all of our plots. We started off with 40 plots. We lost 20 to either a windstorm or some deer or something which knocked them down. Anyway, so we started off with very low values in the spring when the growing season started. Then we have these increases, and then things sort of slowed down. Then we had a rain event, and then they popped up again, and then they slowed down here again, then it rained again, and so on like this. So then we simply summed these measurements with respect to time. So we looked at the summation or the integral of our spectral measurements, and then we compared that to the total amount of wheat which had grown above ground. You can't sample below ground. Well, you can, but it's a terrible pain to do this because you have to wash roots and stuff like this, and it's very time consuming. So we only looked at the above ground mass of vegetation which resulted. And so we had this small thresher, and we had a big crew of people helping us. And from this experiment, it showed that if you have frequent red and near infrared spectral measurements and sum these over time, it is directly related to the total biomass production in grams per meter squared. So immediately you think, wow, how can we do this from satellites? At the same time, someone else published a paper from the USDA which showed that these same red and near infrared spectral measurements are directly and in a highly correlated linear way related to the intercepted fraction of the downwelling sunlight that drives photosynthesis. Otherwise, you wouldn't have had that previous relationship. So from other people, they provided this, which we had shown or strongly suggested was occurring from this figure. So that's why these two are very similar. This just shows you where chlorophyll absorbs very strongly in the blue. It absorbs not quite as strongly in the red, but this is the action spectrum of photosynthesis. So we had one measurement right here and one measurement right here, and we're able to use this very simple difference of those two bands divided by the sum. So my branch head when I came as a postdoc in very late 1975 was Charlie Snetzler. Here's a picture of Charlie. And in my PhD thesis, I worked on spectral resolution, which bands you should use, which spectral intervals you should use, and why if you want to study vegetation. So Charlie told me, why don't you go over and talk to NOAA, because on their advanced very high resolution radiometer, which is not advanced and not very high resolution, they had managed to have the first channel overlap with the second channel, and this negated the possibility of discrete measurements. So this is really a stupid way of doing things, because you're confusing two things and you can't disentangle them. So he called someone over at NOAA named Stan Schneider. So I went over, talked to Stan, and said it would, and showed them what I had for my PhD thesis on the importance of discrete spectral measurements. And so, and I also emphasized they should make these bands much narrower, because if you want to have ex post facto calibration, if you have narrow bands, it's much easier than if you have very, very broad bands. Well, the good news was they split them, but the bad news was they said, for classified reasons, we need to have these broad spectral bands for people in the Navy or for someone. Anytime I hear anyone talk about scientific instruments and there's classified reasons for this or that, I immediately suspect they don't know what they're talking about. Because the laws of physics are pretty simple. Anyway, so they split these bands, and this then made possible to use data from the advanced very high resolution radiometers, who are polar orbiting satellites, very wide field of view. They're spinners, and you get 1 kilometer satellite data at the satellite subpoint from them, but they have a wide swath width. It's really horizon to horizon. Now, because of that paper, which I wrote up and published on our handheld instruments, some people who I didn't know, Charlie Von Pratt, right here, called me or sent me a letter. Back in that day, we didn't have email. You corresponded by letter, and you could work on your composition skills a lot better, and you didn't get in trouble by, as we do with email sometimes. But anyway, so he contacted me and said they had a project in the north part of Senegal looking at biomass in a pastoral system. Would you, and they even paid my way over to come over and bring a handheld instrument to help them do grass sampling. Because clipping, once again, was a giant pain. Well, I was aware of data from NOAA 7, which had just been launched, and so I made requests to get 1 kilometer satellite overpasses of northern Senegal every week or every 8 days, because the orbital period is more or less 8 days from the NOAA polar orbiting satellites then. And so we were working in northern Senegal, and actually in these locales you really need a Land Rover, as opposed to people here who drive them to and from the shopping center usually. But anyway, so we're working there. And one of the really curious things, we were working right here in the northern part of Senegal on the Senegalese River, on the River Senegal next to Mauritania, is you have a pulse rainy season. So this is a monsoonal, because you're a locale, you're maybe 15 or 16 degrees north. And so the rains come and you have a pulse rainy season, dry season, rainy season, and then it ends. So all the rainfall falls in a short period of time, 2 or 3 or 4 months, depending upon the length of the rainy season. And furthermore, there's a really interesting precipitation gradient going from where this blue arrow is down here, about 1 millimeter per year per kilometer in the north-south direction. And this is fairly synchronous with respect to latitude and also longitude, because you have these lines of equal precipitation which then stretch across like this. They just vary depending upon the severity of the rainy season. So in the northern part of Senegal where we were working, this is what it looks like in August just after rain. But there's this marked difference between the rainy season on the right, the dry season on the left, same place, just a few miles or just a few months apart. And then there's also a marked difference between and among years. So here's a picture looking at a particular area in 1984, probably the drought of the century. Extreme events are always good to capture in time series because this provides a lot of information, and it just turns out quite well if in your period of observations you have extreme events. Here was the extreme drought, probably of the century, 1984. Here's the very same area at exactly this, at the middle of the normal rainy season, but 10 years later, and you wouldn't recognize the same area. So this is an ideal place to work because of the variation and because of this precipitation gradient and the pulsed a rainy season of just a few months followed by many months of dry season. When you do field work, you break down, you also amuse the local people. They wonder, why are these people here trying to do this? Don't they know otherwise? But anyway, so here we were sidelined because we overheated the engine from driving through high grass, and all the grass blocked the airflow onto the radiator. The car overheated, and so we had to stop, and this slowed us down. Then you also get stuck because even though it's a pretty dry area, most of the time it does rain, and when it does, if you drive through some of these sandy areas, because the underlying soil types are largely sand, you get stuck. But At the end of the growing season in 1981, 82, and 83, we went out and we sampled areas. Now we're working with 1 kilometer experimental plots, which means you can only get an approximation of how much grass biomass has grown. But this is largely a herbaceous system. They're scattered trees. This is how all the data look. So here we have now from NOAA 7 satellite data, where we then were able to sum over the growing season for these 1 kilometer by 1 kilometer areas. And here we have the end of season approximation of the total dry biomass in each of these experimental plots. And things looked like this. Well, in a large scale field experiment like this was a major success because we thought it'll probably be a blizzard of points, but it wasn't. So this gave us more confidence. So then we started processing more and more data, and the data came to us initially on 1600 BPI magnetic tapes like this. And we discovered that we could take data over several days and combine them because clouds we wanted to minimize or eliminate, whereas our cloud friends, and there are many of you here, would do just the opposite. And so here we have 10 days of data on the left, here we have a month on the right, and the important thing to note is you have much more consistent data in tropical areas because the cloud cover probability is much higher. So then you can go to an unimpressive image like this, but this going from 1981 through December of 2012 involves more than 40,000 orbits of data. Now you have to start worrying about data storage. So we got tired of magnetic tapes, and so we went, on the advice of our friends in Gene Feldman and Norm Curring, to 6 gigabyte optical disk drives. This is a worm drive, write once, read many times. And this was a major advance because instead of having all of these tapes and thousands of them, you could go maybe to only 100 or 200 optical disk drives. And so this is an optical disk drive. Someone found it and saved it, and I made them promise that if they throw it away, they'll throw it away in my office. Anyway, so then we're able to then look at global data, and this is a CWIS image, because in many ways the CWIS project has led in the production of land and ocean data over a very long period of time, starting in 1997 through a latter 2011. So now we're able to look globally. And from the AVHR instruments, we have this record from 1981 through now. And so we have a wonderful data set. And also, I think that the CWIS project was very clever because they have emphasized the beauty contest aspect of satellite images, and they have some wonderful land and ocean images, and this is one of them. Okay, so now we're going to larger scales, and people still say, well, why are you using this vegetation index? Well, this simple difference divided by the sum, this is a summation from Rangamanini, one of my colleagues, formerly at the Goddard Space Flight Center, but now at Boston University, over flux towers, where we're able to look at the total carbon exchange per year, and you see this linear relationship. So one of the things about what we're measuring holds together globally. Now, I'll just show one or two things of some recent work, and I want to emphasize that now all the work we do is dependent upon teams. And I'm very lucky to have several people like Asaf Anyamba, who kindly introduced me, and Jorge Pinzon. I don't know if Jorge is here, but he is the applied mathematician who has made our now 32-year data set. As of the end of June, it'll be 32 years. And when you have a longer time run of a consistently processed data set, even though you may have larger errors than newer data sets, you can infer some very interesting things way before people who are using MODIS data, for example, because you only have 13 years of MODIS data now. And that is insufficient to look at trends and to capture more extreme events. Okay, so working with some people in the tundra, here's a picture of what the tundra looks like if you're not familiar with the tundra. And so we're using data now from NOAA 7, NOAA 9, NOAA 11. We switch back to NOAA 9, then NOAA 14, NOAA 16, NOAA 18. So we're now in 2013 using data from NOAA 18, and we expect shortly to have to switch to the MEDOPS polar orbiters, which also fly the same type of instrument, the not advanced, not very high resolution radiometer, which NOAA gave them. So once again, we go out, we clip areas, we then compare the satellite data. In this case, top, we're looking at MODIS data for each one of these calibration areas on the ground. And then also we look at our data from the AVHR. We have this relationship. They're very similar. Anything we do now with our data, we compare to MODIS data, and if they disagree, then we go back to the drawing boards, because it probably means we're doing something wrong, because MODIS data are much, much better. It's a much better instrument, and it was designed specifically to overcome many of the shortfalls of the instrument which we use. So this is a comparison. This is the average for the entire Tundra zone, which is about 5.6 million square kilometers. And so in blue are the MODIS data, in red are the AVHR data. Here we have grams per meter squared in total biomass, and total plant mass, or phyto or plant mass, from our calibration points. And so these differences on the average are less than an ounce. Now, of course, when you disaggregate these data, in some places you'll have much greater errors. This is just the average here. And this is just showing, now we started in 1981 for the Tundra. We come up, we have just added 2012 right here. And so we're coming along, things are increasing. This is very interesting. Then we have in 1992 the eruption of Mount Pinatubo, which then caused this global cooling, especially at higher northern latitudes. So plants grow when it's warm, and they grow less when it's colder. So what you're seeing here, this decrease in total tundra plant production is because of cooler conditions caused by this volcanic eruption. Then the climate system resets, and then you come up like this. So what we found in our study, and Jorge and I are co-authors on these three papers, but roughly a 15 or 16% increase in total biomass production because of warmer temperatures in the Arctic. From 1981-82 to 2011 and 2010. So now we'll go to 2012 as we have those data. And I want to emphasize again, anytime you do work like this, it's a team effort. So this is our Tundra group. The top three people are from the University of Alaska. You can tell that because they're more warmly dressed than all of us at the bottom, with the exception of Howie Epstein, who is a Tundra person, but at the University of Virginia. So here's Jorge Pinzon, here's Jen Small, who was also an applied mathematician in our group. And then I'm on the far right, but this is a picture taken in Bolivia, so I'm not dressed for the Tundra. But anyway, all work is done by teams now, unless you're doing theory or it's some very unusual project. So we published several papers. We had this paper in Nature Climate Change 2 months ago. And what we showed now is we're looking in the boreal, and as we're looking from 45 degrees north to the pole globally, is here is our satellite vegetation index as it comes down. And so when we're way up here, we're about 70 north. And so in this area, we're in the tundra. We come further south into this area, we're in the boreal forest. We come down further south, and we are in deciduous forest. So there's a lot of information about photosynthesis, which we can record from satellite data, not only from land, but also from the oceans, using very different processing techniques. And what we found in our study was that it's getting warmer, and so growing conditions further north now resemble growing conditions further south 30 years before, because we have a 30-year data set. So this is a somewhat confusing figure, but we're showing how conditions have shifted. Here we're looking at temperature data. So here we're looking at shifts in the boreal zone on the order of 2.5 degrees of latitude. So we're able to average circumpolarly in different latitude ranges. And so if we average from, for the boreal forest, we have these shifts from the early 1980s to the mid 1990s to 2010, 2011 of 2.2 degrees of latitude and 5.2 degrees of latitude respectively in the boreal zone. In the Arctic or tundra region, it's 1.5 degrees from the 1980s to the 1990s, and it's 4 degrees from the mid 1990s to 2010, 2011. On the right-hand side, we're actually using our satellite data, and we have a somewhat different but very interesting phenomena, that if we look in the boreal zone, we see there was a shift of almost 6 degrees from the early 1980s to the mid 1990s, and then only a 6.3 degree shift of latitude from the early 1980s to the late 2000s. Well, just because it's warmer doesn't mean it's wetter. And for plants to grow, it requires warm temperatures and also water. And so we're seeing the manifestation of some areas of drought at these higher northern latitudes from the mid-1990s through now. And then in the bottom, we're looking in the Arctic region, and there we see that you're not water limited, and so therefore you have a small increase from the 1980s to mid-1990s of 2.2 degrees of latitude shift, but from the early 1980s to 2000, about a 7-degree shift. So plants don't grow if it's dry, and if it's warmer, you need more water. Now there's another paper which a co-worker of ours at the University of Maryland has used our data for, and that's Thomas Mueller, where he's looking to see if there's any sort of effect in terms of where a lot of people are. Now this is a very provocative paper, and we weren't sure if what we did was correct. We're going to publish it and then probably be barbecued, and but at least see what happens. So what Thomas has done is he's come into our long-term data set of primary production, and then he's looked in different areas based upon human density of population. Now, these are not very strong relationships in terms of high unequivocal correlation coefficients, but here we're looking in Africa, there's a positive trend. Here's Asia the same way. South America, there's no trend in Australia. Here's Europe, and here's North America. So the point is, when you have a data set like this, people can use it in all kinds of different ways to investigate things, whether there's the CWIFS data set for the oceans or for our data set for the land. So in my voyage of being a bill collector to coming to here today, what I found the most useful is being able to program. Now, I wish that I could do a lot more programming now, but I don't have the time. And I don't understand Python. I thought it was a snake. And also, well, it is a snake, but I meant Python the language. Maybe that's a snake too. And then also, hyperspectral data. People accuse me of being anti-hyperspectral data. That is not true. But in hyperspectral data, you expend all of your degrees of freedom on different wavelengths. Sometimes you want to use the time domain, you want to find spatial resolution, a wide swath width, and many times more wavelengths interferes with the data rate. So the use of hyperspectral data for research, I think, is phenomenal, and I hope we have one in orbit shortly, hopefully from the International Space Station. Then also, we're very fortunate here at Goddard because we work with engineers who build instruments, aircraft instruments, space instruments, hand instruments. So the possibility at Goddard, which is truly unique, is to work with engineers. And I'm glad that a few of them are here today. And then it's really important to publish papers and get feedback and criticisms and explore other opportunities from the community at large. Because when you publish a paper, inevitably, and everyone here who publishes knows this, people will say, well, we found this phenomena with what you, or it's very similar to what you reported, and this is the scientific method, and then you start playing this leapfrog game and you get really far ahead if you hadn't published at all. So I strongly encourage all of us, this applies to me too, to publish the work you do, and then we should all be working towards consistent long-term data sets so we can understand what's happening with climate. I feel very fortunate that I'm able to work in a congenial and dedicated group. People who aren't congenial, we ask them to leave. But it's done as a democracy, not as a highly centralized democracy. And then once again, it's very unique being here at Goddard. So I'll be happy to stop. Thank you for your attention. It's a pleasure to be able to do this a second time after watching Gene Feldman's presentation, Claire's presentation, other people, to sort of see what I should do to improve this. And I hope this is better than the first time. If not, then I apologize.
Okay, we'll take a few questions and comment. Yes,
Actually, two questions. Firstly, is when will you reach saturation when you measure like NDVI? Like how dense the vegetation will be?
Well, it's not really saturation, but because what it tells you is there's no more absorption of the downwelling solar flux. So it's not saturation.
Okay. Like over Amazon rainforest, can you correctly estimate the LEI?
Well, plants are not going to add more green leaf area if there's no light to be absorbed, because that would be a very stupid investment. Not that plants think this way, but it would not be an evolutionary advantage for plants to add more green leaves if there's no more light to be absorbed.
And also a second question is like over sparse vegetated areas. Yeah, and will soil moisture affect it?
Oh yes, very definitely.
But how?
Well, if there's more soil moisture, plants will grow more, they'll photosynthesize more, they'll transpire more.
But will the soil moisture signal kind of contaminate your
No.
NDVI?
No. Not at all, because we're only interested in green leaves and this absorption, no absorption difference by this wave in the red and in the near infrared spectral regions. So it may alter the background spectra, in which case you would have some contamination introduced, but that would be in an arid or semi-arid area. But if you have repeated observations day after day, then you can minimize those. So that's highly unusual, but I'm sure it happens.
Okay, Ralph?
Yeah, Jim, we just crossed 400 ppm of CO2 in the atmosphere, and you showed systematic increases in the biomass over the land areas, over most of the land areas on the planet. How much CO2 is the increase in biomass absorbing? Are you in a position to estimate that? Is it mitigating the CO2 problem?
Well, there's several things going on. Someone just sent me a paper to review using our data set in the arid and semi-arid area where they claim they can see a CO2 fertilization effect. So it could be increasing. But yes, we can calculate how much carbon dioxide is being incorporated. In fact, this is the basis for several models, taking information about the absorbing surface, its persistence through time, looking at atmospheric CO2, the downwelling solar flux, how that varies over time, precipitation, then to compute this. I personally think it's better to measure it directly using satellite data, but there are some very sophisticated numerical models which do this. Now, how much is absorbed? Well, I think the secular increase in carbon dioxide obviously isn't absorbed. So we could just look at that, detrend the data, look at the secular increase, and the difference would be what we are absorbing, or no, what is not being absorbed by plants or in the oceans. Wouldn't you agree, Gene?
Yeah, the other part is any CO2 that's absorbed by plants on land pretty much is going to go back in the atmosphere when the plant dies. It's a very rapid, relatively rapid recycling.
Well, for some plants.
Yeah, but even big trees, if you look at hundreds of years, it's going to go back up when the tree dies eventually.
Or it can be deposited and turn into coal. I mean, that's how. That's one of the problems. That's our fault. That's a different story. But I mean, Jim had quantitative measures of the increase in biomass over various land areas in one of your plots, which is why I asked the question. I wondered if you had your own quantitative estimate of how much CO2 fertilization is going on.
No, but we're working south. So we're starting in the Arctic, and that's something we'd like to do, Ralph. But you need calibration data to do this. So we can do this really well in herbaceous systems, the tundra, grasslands, places like this. If we go to places like forests, we have to use flux tower data and other data, and then it becomes a bit more complicated because you can't directly measure, you have to infer. So someone should be able to do this, and I'll be surprised if they don't, but it's not something which I've worried about or tried to do myself because I'm not quite sure how to do it.
Peter?
In that same plot that Ralph was just talking about, you mentioned Pinatubo and there's a little dip.
Yes.
What happened in 2009? Both your curves dipped there.
Not sure.
They stopped investing. They stopped.
Yeah. See?
Okay, so you're talking right here. I would say this is the natural variability of the climate system. but I mean,
Volcanic eruption in Iceland, maybe?
that was pretty low. Now Ralph knows about that. That was pretty low elevation, was it not?
It was in the tropical, it went up to the tropopause. It just-
Okay, but it was not stratospheric.
2010. It was not, it was April.
Actually, I don't know, but I'll certainly investigate now.
Well, both instruments measured it, so something.
Yeah.
You know, Jim, it's really impressive. You have a great timeline here in terms of technology, going from a handheld detector to ADHR to MODIS. I mean, it's just this great advance in technology. There's also, I noticed you got a Hollerith card in your pocket there.
Oh, yes,
You forgot to use that prop
Yeah.
in terms of data storage.
Yeah, so we used to have a program on punch cards.
And so there's been
Thousands
this
of.
tremendous increase in data volumes, in processing power and so forth. So you know, it's really an impressive increase in technology. But I guess the question, you have a more than 35-year experience with Goddard, so it's kind of a generic question about Goddard. You know, Goddard has culturally changed over the 35 years. I mean, how do you, what would be your thoughts on sort of the, is it better here, technology? Maybe Gene will answer.
He cares about what people think.
Is it a better environment for engineer-science collaboration over your 35 years, or has it gotten worse? Or
Well, I've never worked on any flight projects. I've worked on a few engineering projects, and but they're usually like-minded people working on various instruments. And so I see no difference in that respect. But I understand it's more cumbersome in terms of flight projects. Now this is all hearsay, and I haven't experienced this myself, but this worry about failing implies check, 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 double check. This is what I hear people saying, but I don't know if it's valid, and I suspect it is. You would know better than I.
Okay, Jim?
Yeah, question, and then I'll follow up on that. You attributed 1992 to Pinatubo and a cooling and decrease in productivity. Could it not have just been atmospheric contamination that wasn't corrected in the data set?
We corrected it.
But are you sure you got it all out?
Yeah. I think we got most of it out. There's Remotus here. He's the one who did it. And
well, surface temperatures were cold.
yes.
You know that's true. That's an independent.
Okay,
observation.
Arctic sea ice follows a very similar trend. Of course, in the opposite direction. No, yes, it was increasing, whereas we were decreasing here. So you can look at other data sets. Arctic sea ice, for example, the carbon dioxide data from Point Barrow, Alaska, and how this varies with respect to time, when the growing season started, or when the zero crossing points occurred in the northern hemisphere, spring and fall. So yes, there are some other data sets to look at which do show the very same thing, and especially surface temperature, Arctic sea ice.
So then to answer what Paul asked, what the biggest change that I've seen in NASA as a culture, and you touched on it, is this aversion to risk. The things that NASA was able to do in the 70s and the 80s and the early 90s in terms of how quickly we could respond to do things, new projects, new flight projects. You didn't have this incredibly long lead time before something was done. You didn't have this incessant review process that would just drag missions on forever. People were willing to take a little more risk, I think. And I think that's driven the cost of a lot of things up, and it's lengthened the time to do anything here. And for me, that's been the biggest thing. And it's a cultural thing within the agency.
I would second that. There's a report out called Pioneering by the Space Foundation. It's gotten a lot of attention, and they cite risk aversion as the #1 problem at NASA. I mean, just #1, hands down. So it's...
It's not just manned space flight where you don't want to blow up people, but
yeah, but it's in unmanned as well.
I'll take the last question from Rob.
You had mentioned that you were going to switch to MedOps, even though you had a little short time series from VIIRS. Is VIIRS going to be adequate to carry on this time series?
Well, that's a good question, and I don't know. But I think it's important to have as long a possible a run as you can from the same instruments. Anytime you switch instruments, then the question arises, are you measuring exactly the same thing with the same uncertainty as the previous instruments of a different type? So I would rather have a consistent record from a series of the same instruments, because the AVHRs, what NOAA did was they, through the Goddard polar orbiting environmental satellite, something, it was called POSE. It was across from Building 21. They would order 6 or 7 instruments from ITT, these advanced very high resolution radiometers, 60 or 70 million each, and they'd pop out 6 or 7 at a time. So there were 3 of those that were transferred by NOAA to EUMETSAT for the European polar orbiting satellites. And they're right now on MedOps 1 and MedOps 2, 2 of those instruments are flying. And there's a 3rd one available for MedOps 3. So we're hoping we could maybe have from the AVHR instruments a 35, 36, maybe even a 40-year record if Providence intervenes and keeps them going, or they dodge space debris or whatever it would be. So I prefer that because of consistent air terms, more or less, because you have very, very similar instruments. When you change instruments, maybe you have much better data, and that may bias things one way or the other.
I think we can, Jim will be here for a few more minutes, so if you have more questions or ideas, you can come forward. So next month, we're not going to have a talk, but we're postponing that to July, first week of July. Michael King is coming down, and then Chuck McLean also will give his talk towards the end of July. So please, let's thank Jim one more time.
Thank you, Charles.